Let's Make a Deal is a television game show that originated in the 1960s and is still broadcast today. Its famous culminating contest has become affectionately known as the Monty Hall problem, named in reference to the show's original host. In this portion of the show, a contestant is shown 3 large doors: door number 1, door number 2, and door number 3. Behind one of the doors is a grand prize, usually a brand new car, and behind the remaining doors are gag prizes, which is often a smelly barn animal or some impractical old appliance. Without knowing the contents behind any of the doors, a contestant is offered a choice of selecting one of the doors. Once a contestant makes a selection, the show's host, who knows which door contains the grand prize, opens one of the remaining doors and reveals one of the gag prizes. Now, before revealing what is behind the contestant's selected door, the show's host offers the contestant the opportunity to stay with their original selection or switch their selection to the last remaining door. The dilemma is to determine if it is better for a contestant to stay with their original selection or switch to the other door. At this point, there are 2 unopened doors left, one selected by the contestant and another. Many are convinced that it doesn't matter whether to stay with the original selection or switch to the other door, believing that since there are 2 doors left, the likelihood of selecting the grand prize is 50-50. The question, whether it is better to stay or switch, has been combative when first addressed. Scientific minds demanded mathematical certainty to prove the likelihood of one outcome over the other. But not every problem we face has to be approached mathematically. A keen sense of logic and some inductive reasoning surely helps when determining which opportunity is better. In essence, inductive reasoning is the process of looking at patterns or examples and then making a general conclusion based on the observations. For example, we know that 1 is equal to 1 squared. 1 plus 3 is equal to 4, which is 2 squared. 1 plus 3 plus 5 is equal to 9, which is 3 squared. 1 plus 3 plus 5 plus 7 equals 16, which is 4 squared. Do you see a pattern developing? We can see that the first odd number, which of course is 1, is equal to 1 squared. The first 2 odd numbers added together equals 2 squared. The first 3 odd numbers added together is 3 squared, and the first 4 odd numbers added together is 4 squared. Observing this pattern, a conjecture can be made about its behavior. The sum of the first n odd numbers equals n squared. We can check this by trying the next sequence of the first 5 odd numbers. 1 plus 3 plus 5 plus 7 plus 9 equals 25, which of course is 5 squared. We'll use a similar inductive approach to the Monty Hall problem. Suppose a contestant is not offered 3 doors to choose from, but rather 10 doors to choose from. There's only one grand prize, and the likelihood of guessing that door is 1 out of 10. But then the host reveals what's behind the other doors except for 1. The contestant is then given the opportunity to stay or switch. Let's do this again, except rather than 10 doors, there are 20 doors to choose from, in which there's only one grand prize. The contestant has 1 out of 20 likelihood of guessing the grand prize door. Again, the host reveals what's behind all the other doors except 1, and then gives the contestant the opportunity to stay or switch. We can expand this even further. Let's suppose there are hundreds of doors to choose from. There's only one grand prize, and the contestant has 1 out of hundreds of guessing the grand prize door. The host reveals all the other doors except 1, and then gives the contestant the opportunity to stay or switch. Seeing this develop, what would you do? Stay or switch? Whether there are 10 doors, 20 doors, or hundreds of doors, the logical conjecture would be to switch for a better chance at winning the grand prize. If this pattern seems to hold, then we can reasonably assume it will work for 3 doors. A simpler and more demonstrable way of showing that it is better to switch is by keeping track of a contestant's decision. We do this by creating a small table. Now keep in mind that for the contestant, it doesn't matter which door contains the grand prize because their selection is always a random guess. So let's suppose the grand prize is behind door number 1. If the contestant selects door number 1, the host will reveal one of the other doors. If the contestant stays with door number 1, then they'll win the grand prize. However, if they switch their selection to the other remaining door, they'll lose the grand prize. If the contestant selects door number 2, the host will only reveal the door that contains the gag prize. If the contestant stays with door number 2, then they'll lose the grand prize. If they switch to the other door, they'll win the grand prize. Finally, suppose the contestant selects door number 3. Again, the host will only reveal the door that contains the gag prize. If the contestant stays with door number 3, they'll lose the grand prize. However, if they switch their selection to the other door, they'll win the grand prize. So from our simple table, we can see that there is 2 out of 3 likelihood of winning the grand prize when a contestant switches from their original guess door. This certainly seems counterintuitive when first approaching the doors. It's obvious that there is a 1 out of 3 likelihood of selecting the grand prize, but we overlook that the host's choice of which door to reveal is not random, it's specific. This act allows the contestant another choice, essentially doubling their likelihood of selecting the grand prize.